Hi, good afternoon, guys. My name is Jacob Agui, and today I'll be presenting the preparation of 1-hydroxyletrain and its use in the highly practical synthesis of secondary and tertiary amines from aldehydes and ketones via direct reductive animation. The overview. In a number of reduction reactions, 1-hydroxyletrain, a flexible hydride reagent, can be used to produce alcohols, amines, and their chiral equivalents and esters from aldehydes/ketones. 1-hydroxyletrain is a desirable reducing agent due to its relative reactivity when compared to other silanes, moisture, stability, and simplicity of handling. Scale and optimization. For instance, the magnitude of the scale of the reaction can be run safely depending on the quantity that the flask can receive and start with. Using a 1-liter flask with a round bottom and 3 necks, we started. The situation will become difficult and chaotic if the 1-liter amount is exceeded, which could lead to accidents and injury. An evaluation of the potential risk posed by borotrain, trithoxysilane, silenes, aluminum ethoxide, p-tolualdehyde, aniline acetic acid, and 1 mole NaOH and dichloromethane should be included of the risk assessment for this technique. Extreme caution must be used whenever high temperature reactions are conducted. Fume hood handling is specifically necessary for troxysilane and all other reagents. The checking process. There's a reaction setup on the top left. On the top right, the reaction mixture cooling. In the middle left, there's a product crashing out. And in the bottom right, it's after dissolving in CH2, Cl2. This is all for 1-hydroxyletrain. And in the bottom, it's the separatory funnel for N4-methylbenzoyl and it's after 1 mole NaOH addition. There's 2 reactions in this experiment, and the first one for hydroxyletrain is at the top. We used 1 liter 3-neck round bottom flask, which is 24/40, a reflux condenser, a 5 centimeter 0.5 centimeter Teflon coated magnetic stir bar, and a nitrogen inlet and outlet needle. For our second experiment, for N4-methylbenzoyl, we used a separatory funnel and a 50 milliliter single neck round bottom flask, which is 24/40 joint. The reaction apparatus for 1-hydroxyletrain is a 1 liter 3-necked 24/40 joint round bottom flask with a Teflon coated magnetic stir bar and a reflux condenser is connected. A 24/40 glass stopper is fastened to the side of the neck, and a 1 liter round bottom flask and a rubber septum with a nitrogen inlet and output needle is fastened to the top of the reflux condenser. The entire device is flame dried following the removal of the output needle. The reagents and starting materials, we started with borotrain, and our product was 1-hydroxyletrain. We started with p-tolualdehyde, and our product was N4-methylbenzoyl. For reaction procedure, this will be for 1-hydroxyletrain, and this would be the part 1 of it. This is the reflux condenser is attached to a 1 liter 3-necked round bottom flask with a 5 centimeter and a 0.5 centimeter Teflon coated magnetic stir bar. The side neck of a 1 liter round bottom flask are fitted with a 24/40 glass stopper, and the top of the reflux condenser is fitted with a rubber septum with a nitrogen inlet and output needle. We then remove the exit needle, flame dry, and then cool to 23 Celsius while N2 is being pumped through. Rubber septum will replace the glass stoppers. A part of a flask with a circular bottom has a 6.28 gram of borotrain charged in it. 400 milliliters of xylenes is added through the side neck of a graduated 500 milliliter cylinder. Trithoxysilane 11.1 milliliters should be then injected through the septum using a 20 milliliter plastic syringe. Then 0.12 grams of aluminum ethoxide is injected into one section through the side neck. Although the reaction mixture initially appears black from the aluminum ethoxide suspension, it shortly becomes homogeneous. We then move to a silicone oil bath that has been preheated to 177 Celsius on a hot plate fitted with a temperature probe is used to contain the device after the condenser has been flushed with cold water. We then move to the oil bath at 177 Celsius while being stirred for 4 hours on a reflux. The reaction mixture is taken out of the oil and cooled to 23 Celsius under nitrogen. It is clear and colorless, as we may see. To use 185 millimeters Waterman filter paper and a 1 liter filter flask. An additional 40 milliliters of cold 0 Celsius silanes is used to remove the leftover product from the round bottom flask and rinse the filter cake. On the funnel, a white fibrous substance is still present and is vacuum dried for an additional 10 minutes. Transferred to a round bottom flask measuring 100 milliliters and a stir bar measuring 2.5 centimeters by the 0.6 centimeter in size. A 100 milliliter graduated cylinder is used to add 60 milliliters of CH2Cl2, and then the liquid is agitated for 5 minutes. Collected in a single-necked 250 milliliter round bottom flask, a fine white crystalline powder will result after 30 minutes of solvent removal. To produce 1 hydroxylatrine, the product is dried for 12 hours at a high vacuum of 0.30 mmHg before usage. Now, this is the reaction procedure for N4-methylbenzaniline, a 50 milliliter single-necked round bottom flask containing a 1.2 centimeter 0.8 centimeter egg-shaped stir bar is charged sequentially in one portion with p-tolualdehyde of 1.6 milliliters and aniline of 1.5 milliliters using a 3 milliliter plastic syringe through the septum with a vent needle, resulting in a cloudy opaque solution. Acetic acid in 14 milliliter is added over 15 seconds via a 20 milliliter plastic syringe through the septum, resulting in a homogeneous bright yellow solution. The reaction mixture is stirred, and then 1 hydroxylatrine 4.8 gram is added in one portion through the neck. After removing the vent needle, the reaction mixture is stirred over 3 hours at 23 Celsius, transferred to a 500 milliliter separatory funnel and diluted with CH2Cl2. NaOH, 1 mole is added to the separatory funnel in 50 milliliters portions to minimize an exotherm is used to wash the solution through inversion of the separatory funnel with frequent venting. We then go to the organic layer, which we collect, and the aqueous layer is then extracted with CH2Cl2, and we do this twice, each going for 140 milliliters. Organic layer is washed with H2O, 100 milliliters of H2O, and dried over MgSO4 for 5 minutes with occasional stirring by hand, and then filtered by gravity using a plastic funnel and a 185 millimeter diameter Waterman filter paper into a 1 liter single-necked round bottom flask. Removal of the solvent by rotary evaporation is performed until the volume is small enough to transfer to a 100 milliliter single-necked round bottom flask. Transferring to a 100 milliliter single-necked round bottom flask, additional 10 milliliters of CH2Cl2 is used to transfer residual product from the 1 liter round bottom flask. Final removal of the solvent by rotary evaporation. Then placed in an oil bath preheated to 60 Celsius and further dried under high vacuum 0.3 mmHg for 12 hours. After cooling to 23 Celsius, the resulting solid is washed with cold 0 Celsius petroleum ether, 1 milliliter of it, and after the liquid is removed by trituration, is dried under high vacuum for 12 hours, 0.3 mmHg. The solid product is heated to 50 Celsius on a water bath until melted 5 minutes and then cooled to 23 Celsius while under high vacuum 0.3 mmHg overnight to yield the product N4 methylbenzyl aniline as a pale brown crystalline solid. The reaction workup. For the top left, the scope for aldehydes and the primary amines for DRA to form secondary amines. On the top right, scope for aldehydes and secondary amines for DRA to form tertiary amines. In the bottom left, the scope for ketones and primary amines for DRA to form secondary amines. And at the bottom right, scope for ketones and secondary amines for DRA to form tertiary amines. Purification. Although the products weren't purified, they underwent extra processes that included attempts to separate the finished products and the use of other reagents to make sure that their finished product was evident. As stated before, most of them had a waiting time of waiting for 12 hours just to make sure that they were pure, that they were the product that they were looking for. Characterization and proof of purity. When 18.8 milligrams of pyrazine and 40.8 milligrams of compound were dissolved in 0.9 milliliters of CDCl3, QNMR was used to assess the product's purity. It was established that the purity was higher than 99.5%. A second reaction carried out at the same scale resulted in a substance with a purity of 98.5% and a yield of 73%. By dissolving 13.9 milligrams of pyrazine and 32.0 milligrams of compound in 0.9 milliliters of CDCl3, QNMR was used to assess the product's purity. The calculated purity was 98.9%. According to this calculation of purity percentage, the product's mass is 2.19 grams, which is 82%. A second half scale process produced a 90% yielding product with under 99.5% purity. Safety note and hazard warnings. 1-hydroxysilatrane is a non-volatile solid. N4-methoxybenzyl aniline. If swallowed, it can be harmful. It also is irritating the skin. Also, if it comes in contact with the eye, it can cause severe eye damage. Discussion section. This chemistry lab could be done in our lab, but because there are so many steps, it would need to be broken up into multiple lab sessions. The majority of the supplies and equipment were used in this experiment we have used prior in our lab. Given that I only have lab once a week for 2 hours and 45 minutes, the only challenge would be the waiting period and the continuous times established on this experiment. The authors. First, it's Fawaz Azam. He was born in Malaysia's tropical Penang, and he was in Dubai, United Arab Emirates. He relocated to Toronto in Canada in 2014, and in 2018, he graduated with a bachelor's in science in chemistry from the University of Toronto. He is presently enrolled in Ryerson University's master's in science degree in molecular science, where he does research on new synthetic organic methods that utilize salines. At Ryerson University, we have Mark J. Adler, which is the middle, and he is an assistant professor in the chemistry biology department in Canada. He was raised in San Diego, California, graduated from Duke University and Yale University with degrees in chemistry. He was also trained as a postdoctoral researcher at Yale University and the University of Oxford. Jinsu Ham is at the bottom left. While studying at Korea Advanced Institute of Science and Technology, also known as CAST, for his bachelor's in science and master's in science in chemistry, he conducted research on complete synthesis of natural products in the lab of Professor Hee-Yoon Lee. He spent 9 years working in the industry at SK Innovation before enrolling in the PhD program at UC Berkeley.